Hello! Welcome to the Berkeley Seminar. Today we're delighted to have Dennis Chen, who's a PhD student at UC Berkeley and a regular here at the Berkeley Seminar. And he's going to tell us about Cartesian polynomial monads in homotopy type theory. Thank you, Dennis.
Thank you. So I have been, trying to get into sort of homotopy type theory for a bit. And my main motivation has always been to try to study infinity categories. So just a little bit of background. Infinity categories have been used in various fields of math now. Algebraic geometry has seen like a huge proliferation of techniques. And the whole point of it is because there are certain structures which just have like an infinite number of coherence issues that you kind of have to deal with. For example, in a topological space, they naturally form kind of infinity groupoids. They have like the kind of structures you see is you'll have like homotopy. They're like two spaces can have different maps, but these maps themselves can kind of talk to each other. There's like a higher dimensional morphism, and between two homotopies, you can have more higher dimensional morphisms. Anyway, so humanity has sort of not been able to come up with a very concise way of defining these things, unfortunately, as of yet. Maybe that's a little bit debatable, but one such hope is from the field of homotopy type theory, and I want to give just a little bit of a precursor as to what kind of stuff is in it. It's a Martin-Loaf type theory, so it has two basic objects. There are types, and then you can have things inside of types called terms. There are various type constructors, like given two types, you can take their pair, their Cartesian product, and this is exactly what you think it is. It'll have pairs, one term of each. Those are the things that inhabit such a type. There are function types. There's dependent pairs, which look like this. A, and then B will now depend on A. So these are all pairs such that you can give a little a in the first one, and then your little b will be inside of this kind of dependent family. And there are dependent functions.
When you say A is a type, it might be dependent. There's some context floating around that you're avoiding thinking about.
Yeah, like usually that's the case. For this talk, I think you can just think of just A just by itself, and it'll always be if there's a dependency, I'll always write it like this. You'll see it explicitly. Now the main thing that homotopy type theory kind of has are two things. One is identity type. So given any type A, there's a type of identities, and two terms. There are identities that look like this. Sorry, this is a little scattered. I didn't want this to go on for too long. But this is a new type. And it's basically the type you should think of paths from little a to little b. This is how we're going to think of it semantically. Originally, that wasn't how this was thought. This was just identities, and people thought that there should only be a unique identity witnessing a equals b always. But it turns out that not having that gives rise to some beautiful structure. Okay, so there's such a thing. Let me just say some words about this. There's an introduction rule that says that every A equals A has a guy called the reflector. And there's an elimination rule that basically amounts to saying that the map from A to this path space of A, which is just the dependent sum over all A comma B, this kind of guy, just take all possible paths. There's a map here that says, given any little a, I'm going to map it to the reflector. From topology, we know this is a homotopy equivalence, right? Like a to paths of a, kind of every path, you can contract it back to the constant path. And the elimination rule basically says that if I want to map out from path of a to some x, it's enough to give its values on constant paths. So if I know where all the constant paths go, i.e. where all the reflectors go, it determines everything else. That's one way you can see this. And the last thing that we have is an axiom called univalence, which is an important one. The basic idea here is that we have, floating around we have universes. So all of our types live in some infinite sequence of universes. These are just indexed by natural numbers. And what univalence basically says is it says that given any equivalence of types, this data is the same as giving a path inside of, okay, let's say they both, A and B, both live in the universe U. It's one of those. It's the same as given a path in the universe between A and B. This axiom is what prevents sets, for example, to be a model of this, because in sets, the universe of sets you think of is itself a set. But the universe of sets is like, it's a set. It doesn't remember like this one-dimensional data of isomorphisms between sets. You'd actually want like the one groupoid of sets here for univalence to hold in sets, which is why this axiom kind of fails. This doesn't have enough structure. And then you can ask, okay, what if I took, instead of sets, one groupoids? Well, then this thing, to remember all equivalences of one groupoids, would have had to be a two groupoid. And then you kind of see, it kind of builds up. You kind of need all infinity levels of equivalences for univalence to hold. Okay, but this is a model. It models, the basic objects that it models are homotopy types, which are kind of like topological spaces up to homotopy. And these are like a very homotopy, flavored objects, and people thought that this kind of theory could be used to found infinity category theory. Kind of makes sense. Infinity category theory is homotopical in nature. These are such objects that would help you attack that kind of problem. Now, people have attacked this problem trying to, formalize infinity category theory in this theory for a while, and they ran into a problem. And people, I think this is a folklore name for it, called the autophagy problem. You kind of run into the fact that, infinity categories have all these coherences. Okay, let's use these type theory to talk about those coherences. So we can capture all of those coherences in some kind of type, but that type itself is a type, and it has its own coherences issues, right? Like it'll have its own coherence issues mainly because our equality types are kind of like loose. They're only like up to paths. Paths themselves are like already themselves like a coherence issue. If you compose two paths, you don't have like associator up on the dot. Path composition is only associative up to homotopy. Like you run into, you're kind of just pushing the problem back, if you will. Like coherence issues, push the problem back, more coherence issues, which is unfortunate. But that arises, some people have added various different axioms to homotopy type theory to kind of solve this. And one way to do that is to basically say, I'm going to axiomatize a certain set of algebraic structures instead of trying to define them internally to homotopy type theory so they have like some strict, nice computational laws, so I get to remove some of these coherence issues. Yeah.
We could take a quick breath there. Then it sounds like you're about to now.
Yes.
Start.
Yeah.
I feel like I maybe can't really ask for a useful clarification. Just can I make a play for anybody who didn't study infinity categories in grad school? Ask a question,
Please.
clarification, or comment,
Yes.
summary, or anything. I'm wondering whether maybe this was sort of like many points that like me and David are like, everybody else.
Yeah.
You mean? This might be hard just about.
I appreciate that. I'm wondering if I can do it, but like a paraphrase, like what you got out of the last.
Yeah, so.
Or like not from you, sorry, from someone in the audience.
Okay.
All right, it's me. Okay. There are these things like points, and you can be like, these points have paths between them, but then the paths could also have like paths between them, and then those things could also, oh my god, there's just so many, it goes on forever.
Yeah.
That's about what I have, to be honest.
Can I try?
Yeah.
Dennis wants to understand infinity categories, and there's like a homotopical flavor to them. And so HoTT looks pretty useful. But there's like an autophagy problem, which is somehow the coherences, something aren't as well behaved as you might hope because paths are too flexible. And that's what we're going to talk about today.
Yeah.
Maybe a question I have is, what is coherence? What is a coherence? What is coherence?
Yeah, that's a great question. That's something, yeah.
Is it like a associative block type thing?
Yeah, it's kind of like the problem of.
Identity is an example that many people in here know about for a monotable structure. That's like a two-categorical case.
Yeah. Exactly. So when you have like infinite cells that go on, you have like homotopies between homotopies between homotopies. What happens is like your associator, say like you have composition in a category, it has to be associative. But that associative thing should only be up to homotopy when you have like a two-cell, when two cells exist. So those associators themselves have to satisfy some kind of pentagon law. But if you have three cells, it should only be up to some three cell. But then those three cells have to satisfy some kind of bigger law. But if you have four cells, it should only satisfy up to a four cell. It's like really, really difficult to write down all such things. I think somebody did it for example, week 3 category. Somebody wrote down like all of the laws, and it takes like multiple pages to. Tetra category. Yeah.
Can I try to say that back to you?
Yeah.
So like when I have some sort of associative law, if it's a higher category, it'll be like several of these because the squares be up to homotopy.
Yeah, and then those homotopies.
I get to be like, but that would actually commute.
Yes.
But in an infinity category, I don't get to do that.
You don't get to do that. No.
So like, how is this tractable?
Yeah. How do we study such a problem?
That's cool.
And so that's what you refer to as the autophagy problem. Is that, oh god, we can't write down all these coherences in homotopy type theory or with coherence.
Yeah, it's like in homotopy type theory, even though we have this homotopical flavor, people have tried for like a couple of years now and still weren't able to tackle the coherence problems because it kind of like, so you write down this thing that captures the coherences, it itself has an identity path thing that you have to study, and its path stuff have its own coherence problems that you kind of just push the problem back, I think. Just unfortunate. So the paper that I'm using, Finster, Allioux, and Sozeau, they kind of describe the problem in a similar way. They're like, in homotopy type theory, one can't easily talk about algebraic structures that are like higher algebraic structures, because to talk about such a thing, it's a type, and once again, it's path. It's a type, and its path space will be like incontractable again. So they go about the problem by saying, let's just talk about a certain subclass of algebraic structures, and let's axiomatize it. So instead of having only this type of equality, there's another type of equality in computers, which is called computational equality. That's when your computer can actually just like replace stuff with other things. Like if I have 2 + 2, your computer is allowed to replace this with 4. Like there is no, like inside of the natural numbers, for example. With this kind of path equality, I'll call it that, you can't just replace things. Like it doesn't quite work. You always have to carry this data of this path around that proves, say, that A is equal to B, or that like, you have to remember this path in order to carry things around, which causes all your coherence issues. This is like a strictification. It's like, screw the paths, I don't need them, I can just compute. Like I'm allowed to just replace things willy-nilly, no longer needing like this kind of wavy pathness, which removes coherence issues. And that's the basic idea by these three. They will axiomatize a set of algebraic structures, namely polynomial functors, polynomial monads. And they basically add it onto homotopy type theory. And they'll use this theory to talk about higher structures, which is a beautiful theory because even though those monads are semi-strict, right? We add like some computational laws on top of them, so they're no longer like the freely, completely weak, coherence issues everywhere kind of object. They're still able to talk about those objects with coherence issues everywhere. So the main 3 things that I use is Finster, Allioux, and Sozeau's paper. I'll just call it FAS. A construction that they use on polynomial functors, which is very, very beautiful, is Baez and Dolan's slice construction, which is able to basically take a polynomial functor, and you can talk about relations on that polynomial functor. It is captured as another polynomial functor, which is very beautiful. And okay, HoTT, some HoTT resource, you know, HoTT. The HoTT book is a good one. Okay, so I'm going to start with just talking about what they axiomatize. So they talk about polynomial functors. Well, how do you axiomatize such a thing inside of homotopy type theory? So they axiomatize, well, let's have a universe M of such monads. And given any, so this is a type, I guess. It's axiomatized into the theory. Given any little m, yeah. Is there a question? Yes. It's more seeable. Question? Not yet. So given any m, we have 4 beginning rules. And these rules are basically saying that every m has with it the data of a polynomial functor. So that index, well, this m you should think of as a functor from space over some indexing set to spaces over some indexing. If it makes you more comfortable, you can think of set slice over I to set slice over I. Set here. Here it can be a spaces. Yeah. So that's the cool thing about this theory. Like this theory is really natively into homotopy type theory. It really describes kind of stuff like that. But it's the same kind of flavor. So you'll have an index set of m, which will basically be this underlying set, or underlying type, or underlying set I. You will have constructors. Let me draw a picture. I think this will help. You'll have these constructors. You'll have positions, and you'll have types. And the terminology is a little unfortunate. But this is the basic thing inside of M. We know polynomial functors consist of like these little trees, right? Like those are the things that M has. M has the data of such things. So every constructor has an output type that's labeled by the index. And then it has like a set of, well, it's a type of positions. So unfortunately, they use the term positions for these input positions. And then every input position has like an index, an indexed indicator, basically. So every constructor gives you this kind of data. So M has like some indices, M has some constructors based at a certain index. This is what this is. This is like just telling you the output. And then the next 2 data, the positions and the type, this is saying it has some kind of type of positions, and then every little p inside of the positions is given an input type. So those are the inputs of M, those are the outputs of. Okay, does this kind of data make sense? Yeah. Yeah, there's a bit of a change in terminology, unfortunately. Yeah. I think these are the positions, right?
Index is like the variables, right? These are multivariable.
Yeah, these are multivariable. It's not just set to set. It's set sliced over I to set sliced over I. Yeah. Yeah, these are the variables. Yeah, these are the positions. And then, the positions and the typing data are like the directions. Say, yeah. So the positions are the directions, and the typing data is telling you what the variable is according. Like every direction should have an input type, or what is it? Should have a variable decorating it. Yeah, that their paper used this terminology, and I was too afraid to change from it. No, it's okay. Yep. Oh, I drew a picture here. Yes. Same kind of picture. So yeah, so this data, it's the data that we just saw actually can be done internally to homotopy type theory. Nothing so far has used really, we haven't like used the fact that we axiomatize something new yet.
So we're in the middle of defining the type M of multivariate polynomial.
Yeah. Yeah. So the next data that we need is a unit and a multiplication rule, as we know from monads. The unit is exactly what it looks like. Given any index, given any variable, index I, you will get like basically the unit tree. This is the kind of thing that every monad has. Given any index, it should have the unit tree that does nothing. I'll denote as mu m at I. Okay, now multiplication is going to look a little funkier, but it's basically tree grafting. It's the thing that we all know and love. This data here is saying, take me this bottom constructor, and then for every position of that bottom constructor, give me something, another constructor who output matches the input of that position, so it's graftable. So given this graftable data, I should get a new constructor. I should get a new tree, basically. Given all this graftable data, yeah, that's the kind of thing. OK, so this hopefully makes sense. So now we get to the point where we can now impose some strictness to our data. What we would want, for example, is we want our units, the positions of our units to always only, units should only have one position, right? It shouldn't have more than one position somehow. It shouldn't have more than one input. And similarly, when we multiply, it should be easily calculable that the number of inputs, basically, that our multiplications have is the sum over all of the inputs that we added on top. And this sum exactly captures, you just sum over all of the constructors and then take all of those inputs. That should be true. Now, unfortunately for us, having these as strict type equalities, like computational equalities, doesn't quite work. We can't just let the computer reduce this into that and reduce that into that. And that's just I think the main problem is in homotopy type theory. You have problems in homotopy type theory where like the unit type is not quite the same as the unit plus maybe some big thing and then zeros. There's only an equivalence. Like it's hard in homotopy type theory to get like a judgmental equality of types, a computational equality of types, which is why the FAS people, they decided to only impose a natural equivalence between these two. So we want these two, and then upcoming is how we get that. We basically give like two rules for introduction for this positions of the unit and eliminations for the positions of the unit. And those rules will exactly match the rules for the unit type. So this one says that, OK, this data is always given if you're given a unit. Basically, it says, given this data, there's always a guy called, let me erase some of this. Given, if I'm looking at this unit, I always have a dude called this living inside of the positions of this guy, or the input types. There's always such a guy. That's what the first one says. And it should be thought of as, given my unit type, I have a guy called point or TT or whatever, true, called inside of it. OK, and the second one is an eliminator, which, yes?
I feel like, OK, you introduced what M's are. What
Yep.
are M's again?
The M's are just like, so we axiomatize this curly M, and it just has some, a monad. You can call them monads, yeah.
You're saying, given a monad, I can create the identity monad, and you're telling us how to do that?
Not quite. So given a monad and given a variable of it, it'll always have this thing called the unit constructor of that variable. So given a monad and some I in its index, we always have like this tree, right? If it's a polynomial monad, it'll always have this unit tree. Yeah.
Isn't M the type of multi-category? Where
the type.
index is the object of the multi-category, and that's the unit of each object.
Exactly. Yeah. Yeah. So if you're into multi-category language, this is kind of like the type of all multi-categories. The index are like the objects of your multi-categories, and this would be your identities. Like every object of your multi-category has an identity object.
So you're sort of giving us things that we can do once if I have an M. What can I do with it?
Yeah, exactly. This is how you can. So these are called like decoding rules. Like M is like the code for this data, and then how do we decode this stuff? And this part is just some annoyances that we have to deal with just to say that every identity like this, the number of positions that an identity has should only be one. There should only be one such, one such input to the identity morphism. And the way that they do it is kind of kind of funny. Let me go over the introduction and elimination rules for the unit. I think that would be useful. So the introduction rule for the unit is there's one guy called TT inside of the unit. And the elimination rule is if I've given a type x and I'm given a term inside of x, I always have a unique map from this unit to that x that basically sends TT to that little x. So this is the elimination rule, and that's the introduction rule. So this part basically copies that introduction rule. This data is just part of any unit. You always have to have a monad, and you always have to have a thing to take the unit of. So this is kind of like in the background. This is saying that there's always a guy called npos inside of this. And the second part says, okay, this is like background data. I always have an m and a little I if I'm talking about some unit. This is like the x that I'm looking at. And then saying that given a little guy inside of x at that npos, I get a function. So it's a slightly more complicated than this. The basic structure is like this. So given a type family, because homotopy type theorists really like type families instead of just base types, given this kind of type family, whoops, I should call it U, and given a little x inside of x at this guy TT, I get a unique function from 1 to, I guess I should say, like a dependent function. But it's like the same kind of thing. This function is determined by just where should I map that single point. And this is exactly the same. If I know exactly where this point is mapped to, it gives me an entire function from all of pos of the unit, all of the position types of the unit, to x itself. Yeah, this is just a dependent function. You should think, like, if you don't want to think about this as a dependent function, just think of x as a type, and then this just as a type. OK, cool. So this data gives a unique, well, it basically gives a specified isomorphism between 1 and our guy pos of the unit, which is cool. OK. And here's where this theory actually comes in handy. We're allowed to impose typing rules and computation rules. So this typing rule just says, this is the unit that we're looking for, the identity for this object. The type of any input position should always be I. Like, there should be nothing else. Not only should it be I, it should be reducible to I. So anytime the computer sees this type of thing, it is able to reduce it to just I, which is a thing that you usually don't get in homotopy type theory. But we're allowed to impose this because we're axiomatizing like a new kind of structure. And this helps cut through some of the coherence issues. Similarly, we have an eliminator that says, if I use my eliminator here, this function, if I apply the eliminator to, basically the idea is, let's say we're working with a unit type. If I get this function that I got from doing this data, right? If I have a point in x, I always get a function from 1 to x that maps to that point. If I apply this function p to my little x, to my little t, sorry, it starts from that, to my little tt, it should be x, right? That should be the function that we get. This function should be determined by sending tt to little x. That's basically the second rule. It's saying that if I have a function that's determined by sending my guy to little u, and I apply it to this tt dude, this is the introduction rule. It's the unique guy that lives in my positions. It should reduce to just u. That's what this says. OK, so far, I think we've just basically talked about the fact that this should be contractible. It should satisfy the same rules as a contractible space does, basically. OK. So the next, we talk about multiplication. And what multiplication should satisfy is it should be kind of like the positions of a multiplication should be like a dependent pair. And this is why. If I take like a constructor and I multiply it with C1, C2, Cn. What is the space of like positions for this? Sorry, I should say input positions for this thing. Well, it's a pair. Give me a position of C and then give me a position of Q. Right? It's this kind of pairing data. It's basically a dependent pair. And that's exactly what we axiomatized. So I might go a little faster here. The whole point is that given any P in the positions of the base constructor and Q in the positions of a upper one, so given any P and then Q in this upper guy, so this guy, the constructor here has to match. But given such two pieces of data, you will get a constructor of this multiplied tree. And here's the same typing rule for a dependent pair. I wrote it down in case you want to look at it. And then we have two elimination rules, of course. Given any pair, so given any position, let's say this one, it's PQ, there is a first component and a second component. These are the elimination rules. And that's exactly what this says. This is like background data. This will always happen when you're trying to multiply things. But here, given a position of the multiplied guy, you will always get a position of the base constructor by just taking the first component. Right? So if I have this as one of my input positions, I'll always have this P on the bottom. I can extract that data out. Whoops. And this is just the second component. So there's some background data here. Given any position of my multiplied guy, I'll always be able to also get my second component here. And this so far is just trying to say that the positions of the multiplied guy, I think there's a C in delta. This should be the same as exactly just summing, the dependent pair type of summing everything on top. So take a constructor of my base guy. Sorry, to give me a position of the base guy, P and pos. And then I sum over all the positions of my, or delta sense, like all those constructors. And once again, the reason that we do this is now we can actually impose computational rules that help us cut through coherences once again. This one just says, given the pair determined by P and Q, and take its first component, we should get P back. This one says, given P and Q, and we take the second component, we should get Q. This one is like an eta conversion rule. If we make a pair if we start with like a composed position, it already has the data of P and Q. So we start with such a pair, and we take its first component, and we take its second component, and then we pair them again. This should be equal to P again. This is like almost nothing. But yeah, in homotopy type theory, sometimes you have to like force the computer, tell it to make these reductions. Yeah.
It feels different from like in a category. Like what I hear you saying is like we're doing something like composition, but this is different. Like in a category, if I have F composed G is H, I can't like factor H.
Yeah. So this is not quite composition. We're talking about understanding the positions of a composed guy. So in our formulation, unfortunately, we can't directly just talk about we have every constructor has this data of a set of a type of positions, which is this is the thing that we're trying to understand what happens with this.
When I have a position as P type, like a position of P in terms
Yeah. Yeah, exactly. It's like trying to talk about how to discuss this input, the space of inputs basically. It's the exact same as for dependent pairs. Let me see if I have anything else I want to say there. Okay, so far, we've talked about what we can get out of an M inside of our universe. So given an M inside of our universe, we get all that data that I talked about. The key ideas is just that given M, I should write it down, we get some polynomial rules, which is it has an index, it has that positions, has that stuff. It has a unit and multiplication. And lastly, it has some rules that talks about the positions of the unit and the positions of the multiplication. but it encodes a monad. Now we should talk about what actually lives in this universe. Oh, wait, I forgot. Okay, of course there are unit and associated rules. These are also strict. So we're allowed to impose strict unit rules. This one just saying, give me a constructor and attach to it units everywhere. That's what this lambda thing is. So if I multiply a base guy with units everywhere, I should just get C back. And this is, once again, strict. So this is a very nice part of our theory. We can actually just reduce this kind of statement to C. Similarly, there's another unit law. If I start with unit as my base and then anything on top, I just get that thing back. Whatever delta sent. Like delta is the thing that glues this input to this constructor. That's just saying spit out that constructor again. Nothing happens. And then there's some associative law. This one's a little bit hard to decompose. Basically saying that if I multiply a multiplied thing with this last row, so this one basically multiplies, you basically have two rows. You have like the C here, this row, and that row. This one says multiply these first rows first, and then that last row. And then this one will say multiply the last two rows first, and then multiply the first attached first, and they should reduce to each other. And then there's some coherence with the intro and elimination laws that I talked about earlier.
So you made the associators be judgmental.
Yeah. Yeah, exactly. So these monads, like quite counter to, I guess, intuition, are strict. These monads are like stricter than you would like. They themselves don't encapsulate like the higher coherences. They have all these strict reductions.
Like if you made one of these monads where all of the constructors are unary.
Yep. Yeah, I think it'll be a stricter than an infinity category would be.
This won't model arbitrary.
No, it won't. However, what's nice about them is they're strongly confluent. They have like very nice termination rules. And what's also important about them is what's going to come up, which is the slice construction. That's how we're going to get to weaker things. So we're going to start with these strict monads that are very easy to compute with, that we can actually like do all those rewrite rules and reduce everything and actually compute. And then we're going to add onto it this slice construction that takes monads and like then talks about its relations. And then you can talk about relations of relations and relations of relations of relations. Okay, but first we're going to populate M. So that curly M, we currently have nothing, right? We know that given a little m inside of kind of the big M, we can extract this data. But what is inside of big M? One thing that's inside of big M is the identity monad, our favorite guy. This corresponds to the morphism that takes spaces to spaces. That just does the identity, does nothing. As a polynomial functor, if I draw out the trees, it only has a single tree, which just goes from it only has one variable. I'll just call it t, I guess. It only has one variable, only has one morphism, only has one everything. And that's what this is all saying. There's only one index, there's only one constructor, there's only one position for that constructor, there's only one type that thing could have been. And it satisfies all the laws that you would imagine that it satisfies. Okay, so we have such a guy. The second thing we have is we have pullbacks, which is a very neat construction. So given a monad, what we can do is we can look at, say we have like an index. These are the variables of M as a multi-category. Say we're given like another set that decorates every input, every variable of M. Well, now we can get a new monad that basically is now M, but every constructor, every input and output is now decorated as well. So we have this thing called pullback of M along X. I'll usually write it as M sub X. Its constructors now look like this. Just give a constructor of M. Yeah, its index set, that's a good point. The index set of this is going to be the dependent pairs. So give me an index of M, I inside of index of M. Oh. Yeah, okay. Never mind. Yeah. So its indices are just dependent pairs. So they're basically the same indices of M, but you just add a little decoration, a new decoration by xi. Similarly, the constructors, they're just give me a constructor of M and then decorate every single input position by a new. You just decorate it by all the things given by x, basically. Yeah, so every single input position is now decorated with an extra little x along with a little I. The positions are exactly the same, the types, because the number of inputs, if you will, between M and MX are exactly the same. There's no change in this space of inputs. However, the typing data will now basically says, give me a position, I'm going to spit out both the first variable and the second variable. So this is the extra decoration that the MX gives you. OK, this is a pretty benign construction. I think we can all understand that this probably works. Yeah, there are some unit and multiplication rules. I'm going to skip over that. The main heart of all of this higher stuff is this slice construction. And the idea is that given a polynomial, we can create a new polynomial who talks about like the relations of the original. OK, and here, I guess I'll talk over here. Or maybe I'll use this picture. So let's say we have a polynomial, a monad M. And inside of M, we have all these constructors, C1 through Cn and big C, and there's all of this data. We can make a new polynomial whose constructors, or whose trees, look like this data. Given a composable diagram of constructors of M, these will be like the inputs. It'll be C1, C2, C3, C3, all the way to C. And its output will be the composed thing. So the constructors of this slice polynomial will be like relations that say this tree composes to that tree. Or this tree, this composable grafting of trees composes there. Does that intuition kind of make sense? Yeah.
Suppose I have 3 M things, then I can create a new M thing by somehow being like, does M1 compose with M2 relate to M3?
Yeah, kind of.
I think there was probably
Yeah, I should have drawn more dots, I think.
One term of curly M here, right?
Yes, we have just one guy of big M.
No, maybe there was a level shift to that.
Oh, okay.
I just couldn't tell what font.
Yes. I meant a regular M. M1, M2, M3, and then I create a new regular M that somehow talks about is M1,
Kind of. Yeah, so we start with one M, and this new slice M, from it we can build this slice M. And I'm
we also start with a map from x to I, right? Or like over the
not here. We will later. We will combine those two in a later construction. Here we don't. We just start from some guy in M. We can create a new, so from a polynomial monad, we create a new polynomial monad. That's what this does. And I'm going to tell you what the like just intuitively what the constructors of this new polynomial monad look like. Are these tree things? Yeah, the morphisms, if you will, if you like multi-categories. So what are the multi-categorical morphisms? They will look like this. They will look like a diagram where you give me a composable tree of constructors of M. That's the top. So there might be some big tree, D, and then maybe it composes to E. This could be very, very large. And say that this composes under the multiplication of M to this giant thing, H, I don't know, with a lot of inputs. No.
So in the multi-categorical sort of impression of those as being morphisms, is this like the multi-categorical like composition, basically, of like a whole set of those?
It's like saying that in this guy, the the morphisms are like witnesses to composition.
Right, okay.
And the input of this tree is the list of all of these things, C1, C2, there's D somewhere. This is like the set of inputs, and the set of outputs is H. So this is a kind of a multimorphisms from this to that, whose inputs are the squares that I give, and whose output is that thing.
Cool.
And you can see that this is basically kind of like, oh, what is the two cells of M? This is kind of starting to talk about higher dimensionality cells. And you can repeat this construction. You can take slices of slices of slices. Yeah?
That's on the flag that you have 15 minutes left.
OK. Cool. Cool. OK, I just wanted to talk about a bit of how this works. So now, now let's move out of intuition land. Let's actually look at it. So the indexes of slices of M, it's just all constructors of M, or all morphism of M. So this thing's indices, its object set, if you like, its object set is the morphisms of M. So these things, yeah, that's kind of what I said here, where and then we can have multimorphisms, and we define multimorphisms by basically. This is enough data to give us all the multimorphisms, because we can then compose to get the H. So what we do is we define like trees of M. And how do we define a tree of M? It's just a grafting together of various of the constructors of M, or a composition diagram. There are leaves of the tree, which correspond to taking the unit of M, and then for every node of M, if I have a node D, and I have these things, and I have trees already created, so this is inductive construction. If I have already trees that are graftable, I'm allowed to graft. The second thing is a grafting operation. Yeah, so trees have leaves and nodes, and then you can, well, this node operation is basically grafting on this new node to the bottom of a list of trees. Okay, I'm going to try to go a little faster, but this is the basic diagram, and it's inductive. So I have leaves to start off with, and then given I have leaves to start off with as my trees, and then given a set of trees that graft, yeah, I can compose a new one. And these are like W types, if you've seen those before. But the main point is that our constructors, the constructors of slice, are exactly these tree diagrams. And those tree diagrams encapsulate all of the data that I drew here. Basically this kind of pasting diagram, pasting morphisms together. Okay. And we can define positions by induction. Leaves have no positions. This corresponds to, I think, like the tree that only has an output. I've seen that in like in operad theory before. But those are our leaves, and then our nodes, the formula is fairly simple. How many positions should this thing have? Well, it's kind of composing C at the bottom of like a huge tree. C will give us a new thing, and then this is the rest of the sum of all of the constructors that the tree had already. So we just take all the other constructors and plus one. Yeah. And then here's some typing data. Leaves have no positions, so that typing data is empty. The typing data of the base C of a composed thing should just be C itself. And then there's an induction. If I try to ask for the type of something that was not on the base, sorry, I should call this C. If I ask for the typing data of something that's say over here, I should just traverse the tree and ask. That's an induction. I should just ask for the type of that tree, an induction. Okay? All right. So now we combine those two constructions. Given any monad, we always want to talk about algebras, right? There's like algebras here, algebras there. We should be able to talk about algebraic structures. To do that, well, we want to talk about, in this context, weak algebraic structures. Let me jump down. Okay. Let me see how I wanted to define this. This is just a definition. It's back here. Okay, I guess let me just first talk a little bit about how this definition works. So this is a co-inductive definition, which might be a little wild. But now we're attempting to basically take all the slices of M and put them all together into one kind of algebraic structure. So the slice of M talks about these higher dimensional cells, two-dimensional ones. We can take double slices and triple slices and quadruple slices, and we want to somehow put them all together into one thing. This is going back to our original thing with infinity categories where it has slices all the way up. And one definition that does that is this one, where basically it says an opetopic type of M is going to be kind of like an index family. For every object of M, I'm going to give another object. Kind of draw it on the board. Oh, geez. For every this thing, an opetopic type X will consist of the following data. So it'll have like a carrier family, which just takes the indices of M into U. It's just the type of thing that decorates every object of M with another thing. And then it'll have like an inductive or co-inductive guy, which says that it's going to take another opetopic type of the slice of M, but pulled back to X naught. So it has this, and then there's something on the slice. This, and then something on the slice. And one can see this. Let me just unpack some of this data for M equals the identity. Okay, that's the main guy that we're going to work with anyway. So when M is the identity, what do we have? When M is the identity, M doesn't have any index. It just has a single index. So our first X naught, well, it's just nothing. There's just a type. It's just a type. Okay. Now let's try to look at what this slice thing is. So if we have the identity and we pull it back to X naught, what we get is we get like the identity on X naught. This monad basically has only, it's like this, these are the objects, X naught are the objects, and the only morphisms are identity morphisms. So its trees only look like this, little x to little x, basically. Those are the only trees that it has. Okay, now we take the slice of such a thing. So this is the, so what do the slices look like? They look like compositions of such things. Oh, I get a morphism from every x to every y. So this is like the discrete or indiscrete. This is like the indiscrete. It's like the indiscrete category on X naught. That's what it looks like. Now what does the slice look like? The slice will look like data that looks like this. X naught, X1, X2. These are what my trees look like, because my tree only has one-dimensional things. There's nothing else to compose. And I can compose these into X1 to X naught. There's only a unique way to do so. So this is like the kind of data that the indices of my, sorry, these are not the indices. These are the constructors of my slice. Okay, but the indices. Okay. All right, so X1. Let me just cut through some of the nonsense, if I could. X1 will give you basically data from X naught to X naught to U. This, if we take basically R of X once, and then we take the, what does this give us? The indices on the slice looks like this. It's just a pair, X, and Y. Given any X, Y, there's a unique guy. And this should be thought of as some sort of Hom set. So X1 is kind of giving us a Hom set when this is the identity. Now what we can do is we can take R again, and now we look at what do the slices look on the next level. The slices on the next level kind of gives data like this, which is telling you some sort of composition data. If I have this data of well, I have these Hom sets. I can now decorate these again. I can further decorate these, and I can further decorate this. I just called it F. It'll tell me coherence data between these compositions. And then you can see the higher slices will tell me more higher information about composition and stuff. Now, for all these to work together, there is some extra thing that you need, which is called multiplicativity. Basically, you need these compositions to like give you a contractible answer. It could have multiple answers a priori. This data only just says, give me some u. There is a notion of basically being multiplicative, like is multiplicative, which says that given, given this a constructor of M, and let's say I have like decorators x1 through xn, what an algebra should give us is, given a constructor of M and given like inputs that work well with that constructor, I should get a unique output of x. And is multiplicative just says that this space of outputs that are possible is contractible. So there is only one. And it turns out that if one does this, okay, unfortunately I didn't have time to explicitly work out this example, but if one does this for identity, one can ask for, like, is multiplicative for every single slice level. So if you have what's called a fibrant guy, I have it on the board, I think. Yeah, basically is fibrant is multiplicative on this level, and then the rest is multiplicative as well. You'll get something that's akin to infinity groupoids, which means the fibrant types of identity turns out to be something that's akin to infinity groupoids, which I kind of like draw out here. You have like a carrier of points. You have a carrier of morphisms between those. There are carriers of multiplications. The fact that it's multiplicative on the first level actually forces all of your morphisms to be invertible, which is why they're infinity groupoids. And this paper goes on to prove something beautiful, which is that type itself, one of the universes, pick one of the universes, it's equivalent to a bounded version of these infinity groupoids, which you can define using this is fibrant, is fibrant of identity. So they kind of internally prove that type and infinity groupoids are the same. Furthermore, one can talk about infinity categories just by requiring the first level to not be multiplicative. If the first level isn't multiplicative, the arrows have directionality. They don't have to be invertible anymore. OK. Yeah, sorry for the rushed ending.
Round of applause to the audience.
Yeah.
For being
Thank you. Yes.
One thing that worries me about here is the nature of n. Of course, I can do things once, I can do them twice, I can do them 3 times. But what does it really mean to do them n times? Doesn't the n have to be typed somehow? There, do you have some way of thinking about all the f sub n's for all the n's? Where does n live?
You're talking about like a natural numbers thing?
Well, for example, and
For iterating the
for
slice construction infinite?
come out of
So
the natural numbers have to be.
yeah, so I know in book homotopy type theory, even this sequence of universes, you technically need an external notion of natural numbers to talk about it. Yeah,
It sort of worries me as to how to keep track of all of my types.
yeah, so there's like a theory of, what is it, like dependent type theory, or like 2-level type theory. There's like 2 levels, one like external meta theory of natural numbers, and then to use those, you can talk about the universes.